Now, I said before that we can have stepwise reactions or concerted reactions. And in a concerted reaction, all the bonds are broken and made in one step. And that step would be called an elementary step. But often, as I said, they're stepwise, so we have multiple sequences. Now, the elementary step shows precisely how the bonds are broken and made at the molecular level. So you can't show 15 bonds being broken and made altogether if that's not what's going on at the molecular level. That might involve having, 16 electrons around a carbon atom or something. So what you have to show is first this adds here, then that comes off there, then this other group comes in, and this other group is lost. And those individual steps are called elementary steps. And in fact, there are just a few common steps. And by putting those few common steps together, you can get pretty much all of the complicated mechanisms. Now, for now, we're not going to cover radical mechanisms. We'll cover that next semester. But aside from radical mechanisms, we can account for virtually all the mechanisms we'll do right through until May using just about 9 elementary steps that will become very familiar to you by the end of the year. So, these are the 9 reactions. Acid-base should be a very familiar one to you, even from Gen Chem, but we'll look at it in terms of the flow of electrons. That one I showed before where I did it wrong and then I changed it, that was a simple acid-base example. Sn2 is actually very similar, except the flow of electrons happens at carbon instead of at hydrogen. Coordination and heterolysis are simply making a bond and breaking a single bond. These other 5 all involve pi bonds, and the E2 is a bimolecular elimination. That's what the E2 means. 2 molecules involved in the rate determining step, and it's overall an elimination process. And other eliminations are the nucleophile elimination and electrophile elimination, and you can also have nucleophilic addition and electrophilic addition. So I'll run through those elementary steps with examples next, so you can see the kinds of steps that we'll see in the mechanisms coming up for the rest of the semester and the rest of the year, in fact. Okay, probably the commonest one is the acid-base step, and I've shown you one of those already where I showed, as I said, the one that was wrong and then I fixed it between HCl and CH3 and H2. So notice what happens. We have a bond formed from the nucleophile or base to the H. Remember, a nucleophile is just a Lewis base, so the Lewis base gives a pair of electrons onto the H, and then the H will normally have a leaving group attached to it, and once that leaves, it forms the conjugate base. And the H is now bonded to the original attacking nucleophile. So an example of this might be something like this. So this nucleophilic oxygen has two lone pairs on it, that can attack the electrophilic hydrogen. The fact that this is an electrophilic hydrogen sort of implies that it's going to be a Bronsted-Lowry acid. So that forms a new bond from the nucleophile or base to that hydrogen, and then the bond breaks from the H to the leaving group, and that forms the conjugate base. So SN2 we've already seen in lab, and in fact we're doing another SN2 lab next week where you're synthesizing 4-methoxybenzaldehyde or anisaldehyde from the anion of 4-hydroxybenzaldehyde. And you also did this SN2 reaction where we tested a lot of alkyl halides with reacting them with sodium iodide and looking at rates of reactions. And this, because this all happens in one step, we consider it an elementary step. It's a concerted process. You may remember, if you're in my lab section, me pushing the student off the chair as I got on, so the whole process happens in one step. If it doesn't happen in one step, that substitution process, then it's not SN2, it's something else. And usually the atom, in an organic chemistry class, the atom where the substitution is occurring is going to be a carbon. But these same types of processes can happen on other elements like silicon and things like that. Though they may, you've got to be careful, they can go by different mechanisms. So what's involved here is very similar to the acid base. So what happened before was we formed a bond from the nucleophile base to the hydrogen. In this case, we form a bond from the nucleophile to the carbon. It's the same idea. And then when you break a bond, again, you break a bond from carbon this time to the leaving group. So an example of that might be something, I'm just going to take the example I gave for acid base. Instead of having HBr, I'm going to have CH3Br, and that would be an SN2 substitution. Okay, sorry I jumped suddenly there to having it on the board, but we have something similar to the CH3OH we had before. I've made it CH3O minus this time, so we have actually a stronger nucleophile, but it's the same kind of flow of electrons. We form a bond from oxygen to the CH3, and then we break a bond from the C to the leaving group, and we form an ether over here, and the leaving group's gone. Notice this is the nucleophilic atom. It forms a bond to the electrophilic carbon. Now the next one, coordination, is actually a very simple one. We just need to have one arrow because all we're doing is forming a sigma bond. And the only way you can do that without having leaving groups and so on is if you have an electron deficient atom, which is normally going to be a C+, though you can have other types of Lewis acids like AlCl3 and Bf3. But certainly this semester, this is pretty much the only one we'll see in the coordination steps. And it's a very favorable process because you're forming a sigma bond where before there was nothing. So usually it's going to have a favorable delta G. So here's a carbocation. It's a tertiary carbocation, which you should remember from the lab is the most stable kind of alkyl carbocation. So just forms a bond like that. And that gives us a protonated form of an ether. It's supposed to be a hydrogen there. Now, and we'll often see that in the Sn1 process, which we'll be studying fairly soon. Now, the opposite of a coordination step is a heterolysis step, which I'll cover next. So the heterolysis step, again, just involves one arrow, and it's the opposite of coordination. So instead of making a bond, we're breaking a bond. And so that will normally be uphill in energy, but if ultimately it leads to a more stable product, it can occur. But it's usually going to be not the last step, because you'll normally form something unstable like a carbocation. So this involves, just like the coordination step usually reacted carbocation, the heterolysis step will form a carbocation or similar kind of electron deficient species that we said. So an example might be the first step of an Sn1, at least with an alkyl halide, where we have a leaving group already on. And so there's a typical example. Bond breaks, and we form carbocation. In this case, the leaving group is Br minus. Okay, so next I want to cover the elimination processes.